right, so the second to last section we're going to look at for this week is 8.5 Part 3. So again, in your book, the regular book, they do everything in the same section. In the book that I use, they break it into different sections, so I think that just makes it easier because they break it up more. That's why we're using a different book. So we're going to look at what's called the dot product. We've already looked at how to add two vectors together. And what happens when you add a vector to a vector? What do you get? Yeah? Yeah, you get a vector. You get a new vector. It might point in a different direction and have a different magnitude. Yep, you get a new vector. How about when you subtract a vector from a vector? What do you get? You get another vector, and we did a lot of that on Monday visually, and we did some yesterday numerically. Well, now we're going to look at what happens when we multiply two vectors. Now, when you multiply two vectors, first of all, you don't want to say multiply, because multiplying vectors, there's two ways to do it. When you want to multiply them, you have to say which way you're doing it. One way is called a dot product. The second way is called a cross product. Okay, so it's a little bit different. It's not like with numbers. If you just said multiply 5 times 2, there's only one way to do that. With vectors, there's not. Okay, we're looking at what's called dot product. Okay, so here's two vectors. Each vector has a horizontal and a vertical component. And I know that A is the horizontal because it's next to I. B is the vertical, it's next to J. And we're going to look at how we're going to multiply these together. When we do a real problem, the A's and B's would all be numbers, like 2I plus 4J, things like that. Okay, so the first thing is, what's the symbol for the dot product? The way you write dot product is like that. V dot W. If you write this, V cross W, that's something different. Okay, so that's something we might look at tomorrow. When we do cross product, first of all, that's something that only works in 3D. You can't do cross products in 2D. No such thing. Dot product you can do in 2D and 3D. Okay, so we're gonna do dot product, and today we're only doing it in 2D. Tomorrow it'll be 3D. Okay, so formula to find the dot product. First thing we're gonna do is we're gonna take these two numbers that I just circled, and you're going to multiply them together. So you're going to do A1 times A2. Okay. Next thing you're going to do is multiply these two numbers, B1 and B2, and then you're going to add the result. So multiply the two values for A, multiply the two values for B, and add them up. So let's kind of think about what kind of answer do you get when you do a dot product. What did we just say A1 is? A1 is a what?
Number.
It's a number. How about A2? It's a number. What do you get when you multiply a number times a number?
A number.
Okay, so that whole thing is going to be a number. How about B1? Number, and B2?
Number.
And when you multiply two numbers together,
Number.
you get a number. So now we've got a number plus another number. What do you get when you do that?
Number.
Another number. So when you do the dot product, the answer is a number, like 17. That's what your dot product should look like, a single number. It can be a decimal. It could be a negative number. It could be a positive number. It could be 0. But it's a number. All right, so let's try to find the dot product here. Okay, so they want us to find V dot W. So it's the dot product between V and W. First thing I'm going to do is I'm just going to set that whole thing up. You're going to have something times something plus something times something. Okay. What's going to go in the first two parentheses? Yep.
2i and 5i?
Okay, you're looking in the right spot. But if we go back up,
Oh, just the 2 and the 5.
just the 2 and the 5. So the I is not part of the dot product. It's just the numbers in front of the I and in front of the J. So it's 2 and 5. 2 times 5. And what's going to go in the second two parentheses? Yep.
Negative 3.
-3. So V, then W. -3, then 3. Okay. And if we do that out, what would we get for a dot product? Yeah,
1.
1. So the dot product between those two vectors is 1. Now what does that number do for us? Well, we'll see in a little bit. But that number tells us how to find something. Okay, let's try this way. W dot V. What would go in the first two parentheses this time if we do W dot V? Yep.
Would it just be -3 and 3?
Well, we still want to follow the same pattern where the A values come first and the B values come second.
Oh, so it'd be
5 and 2. So look for the A value, the number next to I, and then the other number next to I. Let's start with W, then look at V. So 5 and 2. And what about the second two numbers? 3 and -3. And what would that dot product come out to? 1. So what do you think that means about the dot product?
Order doesn't matter.
The order that you find the dot product in, yep, doesn't matter. And what property is that? Yep.
Associative?
No, not associative. Associative, you keep the order the same, you change grouping. Yeah,
The commutative?
that's the commutative property. So this doesn't prove anything, but it suggests that the dot product is commutative, and it is. The dot product is always commutative. And that's like normal multiplication. When you multiply, if you do 3 times 6 or 6 times 3, you get the same thing. All right, let's try this one, V dot V. So we're dotting the vector V with itself. What would the calculation look like for V dot V? Kill it.
2, 2, and -3,
2 and 2, -3 and -3. What's another way of saying 2 times 2? 2 squared. 2 squared plus -3 squared. What does that kind of look like? It's missing one thing to make it this, but it kind of looks like something we did yesterday. Yeah? Right, almost as like we're finding the magnitude, almost. You're taking the first number, and you're squaring it. You're taking the second number, and you're squaring it. And then you're adding them up. What's the one other thing you'd have to do if you were actually finding the magnitude? You have to do one more thing there. Yep. You'd have to take the square root. Okay, so we're not actually doing that step. We're just squaring the first number, squaring the second number, and then adding them up. That's what happens when you dot a vector with itself. So if I wanted you to find the magnitude of this vector, it would be the square root of 13. But the dot product with itself is just 13. Okay, and we'll do one more. How about w dot w? Or you write down w dot w. Yep.
5 times 5 plus 3 times 3.
5 times 5, so that's the first two. And then 3 times 3, that's the second. And again, if you think of that in a little bit shorter way, it's 5 to the second plus 3 to the second. It's almost like finding the magnitude of w. Squaring the first number, squaring the second, and then adding them up. You're just not taking the square root. There is no square root to take. So it's 25 plus 9, which gives me a dot product of 34. Any question on that one? Okay, and right now, we don't really know, what does that number mean? Like 1, 13, 34? I'm going to show you what it does in a little bit. Okay, let's try this one. It's written a little bit different, but it's still the same idea. I just haven't named the vectors with letters. I've just given you the numbers. What would be the calculation for the dot product in this one? Yep.
Like the outcome?
No, I want to know the calculation first, and then we'll simplify and get the final outcome. Yeah.
2 times 0 plus 6 times 0?
2 times 0 plus 6 times 0. Yep. Multiply the horizontal times the horizontal component, and then add the vertical times the vertical. And then what do you get if you do that? 0. 0 the number, or 0 the vector? So when we do a dot product, the answer is a vector?
No. So it's just 0.
It's just a number, yeah. So when you do the dot product here, you just get the number 0. Okay. Any question on that one? Now, what other property do we use with multiplication a lot? It's kind of a property where you do multiplication twice. Anyone remember what we call that? Yeah?
Exponents?
No, not exponents. Yep.
Formally?
Yeah, and what's that called in general? That's the distributive.
Oh.
Okay, that's the distributive property. So when we do dot product, the distributive property works. Okay. And you might think, well, yeah, you can always do distributive property. No. When you're learning about vectors, you can't assume that anything you know how to do with regular multiplication works with what we're learning. With dot product, a lot of it does. Commutative works and distributive works. But when we get to cross product, you're going to see that commutative property does not work, which is kind of different. Usually you're used to when you multiply two things together, you can switch the order and you always get the same thing. That's not true when you do cross products. Okay. So this is showing that if you take vector u and you wanted to find the dot product with the sum of two vectors, you could distribute the dot product of u with v plus the dot product of u with w. just like that. All right, so let's say I had two vectors and I draw them with the same initial point. I've got one vector like that, and then I got another vector like that. Let's say that this is vector v, and that's W. You'd be really cool if you knew how to find what in that picture. People would just think you're amazing. What? Probably people like me, yeah.
The distance between two like arrows.
Well, we know how to do that, right? That's the magnitudes. So we know how to find those two magnitudes as long as we know where we're starting and where we're stopping. We could make a right triangle like that and do Pythagorean theorem. But thinking of something else. Yep. The angle. Yep. We're on the same cool wavelength. Yeah. So find the angle. All right. So that is what the dot product is going to help you figure out. The dot product is not the angle, but it helps you to find the angle. So this is the formula for the angle. So the formula for the angle involves three different things. The dot product, and then what's in the denominator? Two magnitudes. So you have to find the dot product and find the two magnitudes, and that's equal to the cosine of your angle. So in the last step, we do have to get rid of cosine, but that's something we've done before. Now, technically, you don't need that formula. You can do it without it. Let's think of let's get a piece of graph paper. Maybe something like that. That one's too small. Let's do this one. Right. Let's say that I had a vector like that, and another vector like that. And I wanted to figure out the angle between those two vectors. This formula is the fastest way to do it. But if you didn't have that formula, what do you think we could do with that picture? Oops. To try to find that angle? Yep.
Make right triangles.
Make,
Like find the magnitude of one vector and then the other one, and then you can make another right triangle to find the hypotenuse. You can make like
and now how's that going to help you figure out this angle? Yep.
If you make triangles out of both the sides and then subtract 180 by both of those, you can find the middle angle.
All right, so we definitely want to make some triangles, right? We could think of it, we could start with that. So now we've got a triangle. And we could figure out how long those two black sides, those two vectors are, by making triangles like this. That would enable me to figure out the length of that side in purple that I just drew. What theorem would I have to use to do that? Right. So I could find the length of this side using Pythagorean theorem. I could find the length of this side using Pythagorean theorem. And how could I find the length of the other side that I drew?
use the two found lengths. Yeah.
So we'd have to draw a triangle one more time, like this, and then do Pythagorean theorem with that other triangle. So if I did Pythagorean theorem 3 times, I could find the length of each of these sides. What law could I use if I knew all the sides in a triangle to find an angle?
Side, side, side.
Well, it is a side-side-side triangle, which falls under one of two laws we learned. It's the law of, yep, cosines. Yep. So to find this angle without this formula, you've got to do Pythagorean theorem 3 times. This doesn't take that long, but you'd have to do that. It might take like a minute or so. Do all that. Then you'd have to do law of cosines. That's going to take a little bit longer to find this angle. This formula does all of that for you. That's what this formula is doing. It's basically doing the Pythagorean theorem 3 times. It's doing the law of cosines. That's why there's a cosine there. But it's simplifying the entire result, so you don't have to do that much work. But that's where this comes from. Right? So the entire problem turns into 3 much simpler steps than that. Find the dot product, find the length, find the length. So you still got to find 2 of the lengths, but you don't have to find the 3rd one, and you don't have to do the entire law of cosines. Okay, so it's the dot product divided by the product of the length of u times the length of v. Okay. So let's see if we can find the angle between these 2 vectors. What I want to do first, though, is sketch them and just kind of eyeball what we think the angle is, and then we'll actually find it and see if it seems reasonable. So 4i minus 3j. So that's a vector that goes right 4, down 3. So start here. Let's see. 1, 2, 3, 4. 1, 2, 3. So that vector looks like that. And then the other vector is right 2, up 5. Right 2. 1, 2, 3, 4, 5. So kind of like that. What does it look like this angle might be?
120.
100 and how much?
20.
120? Yeah, it's definitely bigger than 90. So somewhere could be 100, 105. I don't know if it's going to be as big as 120, but it's definitely bigger than 90. So let's figure out what it is and then see if we get an answer that's bigger than 90. Okay. So what's the first thing that I need to figure out to be able to use the formula to find the angle? Yeah.
The magnitude of u and v.
Okay, we could do those first, the magnitude of u and the magnitude of v. And what's the other thing we're going to need? Yeah,
The dot product.
the dot product. We could start with the magnitudes. Okay, what's the formula, or what's the expression we're going to write down for the magnitude of u? Yeah.
4 squared plus negative 3 squared.
Yep, 4 squared plus negative 3 squared. And that's going to give me the square root of how much? Yep, 25. So the length of u is 5. Okay, so there's one thing we need. Okay, what's the formula for the magnitude of v? Yep, Julia. 2 squared plus 5 squared. And that's going to be the square root of 29. We're just going to leave that one. Okay, don't round it off if you don't need to. And the other thing we need is the dot product. What's going to be the calculation for the dot product? Nick, can you tell me what the calculation would be? Swap them out. What's going to be the first two numbers we multiply? Yep, Boris.
4 times 2.
4 times 2. So the horizontal of the first, horizontal of the second. And how about last two numbers? Luke, can you just wait for Steve to come in?
Yep.
Yep.
-3 times 5.
-3 times 5. Okay, so that's going to give you 4 times 2 is 8. -3 times 5. What's 8 minus 15? Yep, -7. Okay, so we've got everything we need now to find the angle. Fill in the 3 values we just found here, and then in the bottom. So it's the dot product over the product of the magnitudes, and set that equal to the cosine of your angle. So dot product over the product of the magnitudes. Now that's not the angle. That's the cosine of the angle. How are we going to get the angle? Yep.
Should the 5 and 29 be in parentheses? Or the 5 and square root 29?
You can, but that's okay like that. I mean, I could also put a dot between them if I wanted, but I don't need that.
But
dot.
they are being multiplied.
Yep. They'll be multiplied without it. So how are we going to get the angle instead of the cosine of the angle? Yep, inverse what? Take the inverse cosine. So that leaves you with your angle on the left. And our right side is the inverse cosine of that. So we're hoping we get a number somewhere between 95 and 110, maybe 100. We'll see what we get. So inverse cosine of -7 divided by. Now, when you type it in the bottom, make sure you do it like this. Why did I type it in like that? Yeah?
Because you want the 5 and square root 29 to multiply before dividing by 7.
Right. I don't want it to do -7/5. That's not what I want it to do. I want it to do 5 times square root 29 first. That's all together, and then divide. That whole thing is in the bottom. Okay. And that looks reasonable. We get an angle of 105.07. That's the angle I'm talking about right here. 105.07. Okay. Any question on that? Okay. Yes.
So the way we did it here, we wouldn't need to do Pythagorean theorem out 3 times.
No, we didn't.
Okay.
Nope, and we didn't do the full law of cosines either.
Yeah.
This formula is a shortcut.
Okay.
We didn't exactly prove why that's the formula. That takes a few steps to go through.
Yeah.
But that is the formula. All right, now, that angle that we just came up with, 105.07, that's nothing special. That's just a random angle between 2 vectors. There is 2 angles that are special. Anybody have a guess? If the angle came out to this number, we would consider that to be a special angle between the 2. Yep.
30.
So 30 is a common angle, but no, nothing with 30. That's simpler. Yep. 0. Yep. We're going to talk about what happens when the angle is 0. What other angle do you think we'll talk about? Yep.
90.
90. Yep. Let me start with 90. So 90 means that the 2 vectors are perpendicular to each other. When 2 vectors are perpendicular, the word they use to describe that is orthogonal. That's how you say that. Orthogonal. So if I ask you on the test, are the following vectors orthogonal, and you ask me, what does orthogonal mean? I won't tell you. You need to know that orthogonal means perpendicular. And a lot of times you might see me use this symbol. If you remember that from geometry, like an upside down capital T, that means perpendicular. Okay, so I didn't write it, but we did just say it. What's the angle if two vectors are perpendicular to each other? 90. So think about what would happen if the angle was 90. Here's your formula for finding the angle. Cosine of your angle equals the dot product over the product of the magnitudes. I don't even know what vectors we're working with, but let's just say we're working with some vectors and the angle is 90. So let's fill in a 90 here and see what happens. Cosine 90. And if they were perpendicular, let's see what the cosine of 90 comes out to. Cosine of 90 comes out to 0. So if two vectors are perpendicular, we would end up with a 0 on the left side of our formula. What would be on the right side? I have no idea. We'd have the dot product over the product of the magnitudes. I'd have to know what the vectors are. But what's the only way that you could ever have a fraction equal to 0? What has to happen in your fraction, in a division problem, for the answer to come out to 0? Yep.
The numerator has to be 0.
The numerator has to be 0. Anytime you have a fraction and the number in the top is 0, then it automatically makes the whole thing 0. Don't even have to worry about the bottom. So when two vectors are perpendicular, we don't have to worry about the bottom at all. All you have to do is check, is the top 0? And what's in the top? The dot product. If the dot product comes out to 0, that's going to force the entire fraction to come out to 0. And if the fraction comes out to 0, that means you must have had an angle of 90 degrees. It's the only way you could get a 0 on the left. Okay, so it's really quick to determine if two vectors are perpendicular. If the dot product is 0. That's it. So let's look at these two vectors and let's see if they are perpendicular or orthogonal. What's the calculation for the dot product? Yeah.
2 times 1. 1 times 2.
2 times 1 and 1 times 2. What do you get for a dot product when you do that? Yep, you get 4. So are these two vectors orthogonal? No. And if you think about graphing them, graph them. They won't look like they meet at a 90. So the top vector is right 2, up 1. The bottom vector is right 1, up 2. Do those two vectors look like they make a 90-degree angle? No. What could you change if I allowed you to change one thing here to make them orthogonal? What could you change? Yep.
You could turn the plus j into just a 0 for b.
You could turn, so you're telling, so well, let's write all these numbers down. Are you changing something in V or W?
You could do even more.
Okay.
Just make the 1 to a 0.
Make this a 0?
Yeah.
What's 0 times 2?
0.
What's 2 times 1? What's 2 times 1? 2. What's 2 plus 0? So that wouldn't be perpendicular, because we didn't get a dot product of 0. Yep.
If in W you made either the 1i or the 2j a negative, when it multiplies it could be -2. Then -2 plus 2 is 0.
Yeah, you just have to make one of those 4 numbers a negative, and then they would be perpendicular. Any one of them. This, or that. Pick any one of those things a negative, and then they would look perpendicular. Any question on that? So 90 is a special angle, and what did we say another special angle is? Yeah? 0. So an angle of 0 between 2 vectors would look kind of like this. That's an angle of 0. It's like if you were to line these 2 vectors up, and I said, what's the angle between them? Well, 0, because they're right on top of each other. What do you think we would call these 2 vectors? They're parallel. Now, 0 is not the only angle that gives you parallel vectors. There's another angle that's also parallel. Yeah?
Would be 360.
Well, 360 would kind of be the same as 0, because you could just add or subtract 360. And that'd be the same as like 720. But like a different angle. Yeah?
180.
Yep, 180. 180 would look like this. And you could think of it as if you connected them. Again, what I did here is I lined up the initial points. That's how I got 0. Line up the initial points here. And now look at your angle. That's a straight line, which makes 180 degrees. So that's the other special situation. If 2 vectors are parallel, the angle between them is either 0 or 180. So let's try our formula and see if we can come up with a shortcut for parallel. What's on the left side of our formula to find the angle? Yep. Cosine theta. And what's on the right side?
The dot product.
Dot product over something about the vectors.
Oh, the magnitude.
The magnitudes. Product of the magnitudes. Okay, so let's try filling in a 0 for the angle and see what the left-hand side turns into. Okay, so we fill in 0. We get 1 on the left side. So you would have a fraction equal to 1. How can a fraction come out to 1? What has to happen? Yep.
If the numerator and denominator are the same.
Right. The numerator and the denominator have to be the same. But the only way you can know they're the same is if you actually know what the numerator is and what the denominator is. So no, there's really no shortcut here. You have to know both. You can't tell if they're the same if you don't know both. Right. Let's see what happens if we put in a 180. Let's take cosine of 180. We get -1. So this is the other case where the vectors are parallel. This fraction would come out to a -1. How can a fraction come out to -1? Yep.
The numerator is a negative over the denominator.
Right, you're dividing 2 numbers that are opposites. But again, to know if the numerator is the opposite of the denominator, you have to know both the numerator and the denominator. So we have to do out a little bit more work to determine if they're parallel. All right, so we're going to figure out if vectors v and w are parallel. Sorry, let me put that back. Right there. Okay, let's start with the dot product. All right, what do we multiply first to figure out the dot product? Yep. So we got 4 times 20, which is how much? 80. Plus, what's negative 5 times negative 25? Yep. 125. And that gives us a dot product of how much? Yep. 205. So at this point, I can't say if they're parallel. I don't know yet. But I can definitely say that they're not what? How come? Yeah?
Is the dot product 0?
We didn't get a dot product of 0. For these to be perpendicular, we would have had to have done the calculation out and got a dot product of 0. We didn't. So they're not perpendicular, don't know if they're parallel yet. Okay. Magnitude of V. Okay. What's going to be the two numbers I add up under the square root to find the magnitude of V? Okay.
Would be 4 squared plus negative 5 squared.
Yep, just going to do that out. So 4 squared plus negative 5 squared. That's going to give me the square root of how much? Yep, 41. So we get the dot product. We've got part of the denominator. We need one more. Magnitude of W. What's going to be the two numbers that I add up under the square root for magnitude of W? Caleb?
20 squared.
20 squared. And how much is 20 squared? 400.
400.
And
25 squared.
25 squared. What's 25 times 25?
5.
Yep.
625.
625. Okay, add them up, and we get the square root of 1,025. Okay, we've got everything calculated that we need to determine if they're parallel. Okay, so let's set up the formula. What goes on the left side of the formula to find the angle? Cosine of theta. And what's going to go in the top on the right side? Yep.
205.
205. And what goes in the bottom? Yeah.
Square root of 41 times the square root of 1,025.
Square root of 41. Square root of 1,025. So if these vectors are parallel, what am I hoping the bottom comes out to? And this is a positive times a positive. So I know we said there's two cases for parallel. Well, there's only one possibility for the answer here. Yep.
If the bottom would equal 205.
Right, the bottom has to equal 205. So let's see. Square root of 41 times the square root of 1,025 gives me 205. So now I've got cosine theta equals 205 over 205, and we've already reasoned out what happens from there. Because they're the same, I'm going to get an angle that makes them parallel. Is there any question why those are parallel? So the two vectors are parallel. So what the questions say? Determine if V and W are parallel. So we would write, yes, V and W are parallel.
How Are you able to determine if they're 0 or 180?
Yeah. So what's 205 divided by 205?
1.
1. And how do you get rid of cosine?
Square, that. Inverse. Cosine.
Take the inverse cosine. So now those cancel out. If you take the inverse cosine of 1, you'll see exactly which situation it is. It's the angle where there's 0.
But aren't you taking the inverse cosine of 1 each time you do that? Like even if it was like anytime it's parallel, wouldn't you be taking the inverse cosine of 1 each time?
Or negative 1.
Oh, it's 1 or
Yeah.
Okay.
The bottom would never be negative. It can't be.
Alright.
Because the bottom is a distance times a distance. Distance times distance is always positive. So bottom would always be positive, but the dot product in the top could come out to a negative. Dot products can be negative. Yep. So the only way you'll get negative 1 is if the top is the opposite of the bottom, and the top will be negative. Any other questions on that? Yeah.
So the paper still goes into the
Um, yeah. All right. So homework tonight is on 352. Okay, it's question 25, 7 through 17 and 25. Actually, you know what? It's just 7 to 17. Each question on 7 to 17 has 3 parts. The first question is find the dot product. The second part is find the angle. And the third part is determine if they are parallel, perpendicular, or neither. So all 3 parts are connected. Dot product, angle, and then parallel, perpendicular, or neither. And we'll take a look at that tomorrow.